Hello everyone, I'm Siegfried Ludwig and I'm presenting our neurogenetic algorithm. It's a spiking neuron implementation of genetic algorithms for optimization. First I'm going to give a short introduction, show the high-level architecture of our implementation. We have two designs, a sequential design and a parallel design. And then we perform an analysis of the complexity of the two designs and have a short discussion. Neuromorphic computing is hardware implementations of neural processors, so basically implementing artificial neurons in hardware for massively parallel and energy efficient processing, and with the added advantage of memory collocation. Usually leaky integrate and fire neurons are used there, and this is also the type of neurons that we use for this genetic algorithm implementation. So the overall advantage of neuromorphic computing is the processing efficiency. And because of this, people started trying to implement non-learning conventional algorithms as spiking neural networks so that they can be run on neuromorphic hardware. So this has been done for sorting, for constraint satisfaction, shortest path, and neighborhood subgraph extraction, among others. And we are here trying to implement a genetic algorithm as a spiking neural network, so it can potentially be run on neuromorphic hardware. Genetic algorithms are an optimization technique that represent potential solutions as genetic sequences called chromosomes. And then you have a pool of individual solutions and you run evaluation on them, fitness evaluation, selection, crossover, mutation in a generation loop to resemble natural selection and evolution, which should improve solution quality over time and can search through a large solution space efficiently. So this is the high-level architecture of our design. You can see that it's basically a recurrent spiking neural network, and here are plugged in the different ensembles that we need for the genetic algorithm. It starts by initializing the different chromosomes. In this diagram it's 8 different chromosomes. You can see every chromosome has a different arrow here, but we can also easily expand this to more chromosomes. So the chromosomes are initialized, then go pairwise into the evaluation ensemble. The design here uses a sort of pairwise setup where we evaluate 2 chromosomes together and say which chromosome has a better fitness, and then we use a single bubble sort step to swap them accordingly to their relative fitness evaluation. So in this sense, at every generation loop, we sort by one bubble sort step, which makes it more efficient than a full sorting and allows this compact implementation. And over time, still the better chromosomes should reach the top lanes here. So this architecture represents a fitness hierarchy where the top chromosomes have higher solution quality and the bottom chromosomes have less solution quality. So the chromosomes are evaluated against each other and go into the bubble sort step. And then they are connected to the crossover, which is basically the reproduction. 2 chromosomes come together and get combined in a new way. And that also happens pairwise. Then each chromosome individually goes into a mutation ensemble before connecting back to the evaluation and forming the generation loop. So we have 2 designs for this, a sequential design and a parallel design. The sequential design represents a chromosome on a single spike train over time. So at each simulation time step, the one bit of the chromosome is spiking on the spike train. The chromosomes then get passed through the neural ensembles. So shown here is the evaluation ensemble and the bubble sort ensemble. Both of them get 2 chromosomes as input and give the same chromosome as output, but the bubble sort swaps them if necessary. Then we have here the crossover is implemented at a random point, so a random gene location is chosen at every iteration, and then the chromosomes are crossed over against each other from that point on. And then we have here the mutation ensemble as well. These ensembles just get repeated if we want to use more chromosomes. Then we have all the ensembles put together into one lane. So the chromosome gets processed, first evaluation, bubble sort, crossover, mutation, and then connects back. And this forms a full neurogenetic algorithm that can run fully also on neuromorphic hardware. So here we see an animation of how the chromosomes get processed over time. You can see here every pixel row is a spike train of a separate neuron. So you can see here the full neural network, and the columns are the time steps of the simulation. So it's basically showing a spike train over time here. And you can see how the chromosomes get passed through into the ensembles, which are shown here row-wise, so you have them processed. So here we have the parallel design. Every gene here is processed at, in one time step by a different neuron. So the full chromosome is processed in one time step as opposed to over time in the sequential design. This of course requires more space because it needs much more neurons and also more connections than to process the chromosome. But the generation time is always the same no matter how long the chromosomes get, because everything is processed at once. Here we have then the crossover and the mutation. And of course they get connected in the same way and give the same algorithm as the sequential design, just implemented in a different way. So we conducted an analysis of the time, space, and energy complexities. Energy here defined as the number of spikes per generation. And that's interesting because in neuromorphic computing, usually a spike needs energy, but no spike doesn't require energy. So it's interesting to see how many spikes we need per generation to implement this. And we found a space-time trade-off between the sequential and parallel designs. Sequential design just means that each chromosome is processed sequentially, but separate chromosomes are still processed in parallel, making use of the massively parallel design of neuromorphic computing. So this is just with regard to single chromosomes. The sequential design is linear in the chromosome length, linear time complexity, because of course chromosomes get processed over time, but doesn't expand in space requirements with longer chromosomes, while the parallel design is constant in the time execution, but expands quadratically in space with the chromosome length with regard to the needed connections, and linearly in space with regard to the needed neurons. So there's the space-time trade-off between the two designs. Analyzing the solution quality just as a sanity check that the that the genetic algorithm is actually working. We have the 1-max problem, so the chromosomes are initialized as zeros, no spikes, and the fitness then is trying to reach once a fully active spike train. You can see here on the left the spike train cut into multiple rows for the space requirements here, but we can see that the solution quality improves over time by seeing more spikes in the image here. And on the right you can also see just the 1-max score of the average of the chromosomes, and that's the blue line, and the orange line gives the top chromosome. You can see that the top chromosome usually has higher fitness than the average, which means that our ranking hierarchy is working and selection is then also possible, because of course you want to preferably reproduce the higher fitness chromosomes. And you can also see that the orange line after about 15 generations here reaches the full 1-max of chromosome length 8, so 8 spikes. So the best solution can be achieved. In summary, we implemented a full genetic algorithm as a spiking neural network, so we can potentially run it on neuromorphic hardware in an efficient way. And this is also working. For future research, an open question is how to implement the evaluation ensemble, because in this current design we need a handcrafted evaluation ensemble for every application problem. So if we don't want to evaluate on 1-max, we need to implement a new evaluation ensemble to run it in the same neural network. So it's an open question how to implement that. Maybe training of neural networks, spiking neural networks, can be used as an approximation to the fitness function. And here's also the link to our GitLab with the code and the simulator we used. Thank you, and I'm here for questions.